Good afternoon, everyone. In the last class, we spoke about ISAs, and today we are going to start talking about pipelining. So what we are going to cover in today's lecture and the next lecture should mostly be review material for you. So we are going to go the 5-stage pipeline, the classic 5-stage pipeline, and then we are going to generally discuss about it, and that's going to lay a foundation for what we are going to do next. So we are going to talk about superscalar and eventually out-of-order pipelines in great detail. Okay. So these two lectures are going to be fairly quick paced because I'm assuming that most of you have already seen a 5-stage pipeline. But if you have any questions, feel free to stop me and ask the questions. Okay, few announcements. So the Piazza thing should be clear now. You should have gotten an email saying which is the right Piazza forum to use. So just go to that one. So that should be clear from now on. If you have any questions, let us know about that. So we've started putting up the lecture recordings on the course website. So if you go there in the lectures tab, you'll be able to see the recordings. So attendance has been okay so far, but if attendance goes down, we're going to pull the lectures. So it is on you to make sure that your friends are attending the lectures, right? So in some way. Yes, the third thing is that the first quiz is due today. So make sure you have read the paper and you can take the quiz. The third quiz, based on the paper that will be assigned today, is going to be due next week, and the quiz will be posted tomorrow morning, by tomorrow morning sometime. Yeah.
Can I make a comment about first quickly? I guess the questions were so detailed that 1 minute per question was a bit.
I see. So did all of you feel that 1 minute is too less?
Yeah.
Okay. So we'll think about it. We'll maybe increase it up. This is the first time we are trying, so thanks for the feedback.
Yeah, because just reading the question took more than 1 hour for sure, and then you have to think, more than 1 minute.
Yeah. Okay.
It's possible that would be.
Okay, that's fair. We'll see what we can do. Okay. Yeah. Thanks. Yeah, we'll see. If we are going to make any changes, that will be made starting with the third quiz, because the second quiz is already out and we want it to be fair to everyone. So if somebody is already taken, then okay. Yeah, thanks. Any other questions on administrative stuff? Okay, cool. So before we had pipelining, we were still building computers, right? And the way we were building those computers was mainly this design, which we call single cycle, right? So the idea behind single cycle machines is that you are going to execute one complete instruction every cycle. So all of the work that needs to be done for a given instruction will be completed in one cycle, no matter which kind of instruction you need to execute. So the good thing about single cycle hardware is that your CPI is very low. It's 1, because every instruction is going to just take one cycle. But the downside is that the cycle period or the cycle time of that processor is going to be very, very high, right? Because any instruction that you might execute on the processor must finish in one cycle. So the cycle time will be determined by the slowest instruction that you have, right? So in order to not incur that kind of delay, we had these other processors which were designed, and they are based on this principle called multi-cycle. So the idea is that we are going to break up the work of an instruction into multiple smaller components, and we are going to execute these smaller subtasks for each instruction in a given cycle, right? So that way you might take more cycles to finish a given instruction, but your cycle time is going to be much shorter than before. So that way hopefully you'll come out ahead, right? So that is the idea behind multi-cycle, right? But the thing with multi-cycle is that you're still executing only one instruction at any given point in time. So you take in an instruction, and then it will take you a few cycles to finish that instruction, and once you're done with that instruction, you move on to the next instruction, right? So people looked at these two designs, and then they were wondering if we can do something better, and that is where pipelining comes into the picture, right? So the motivation for pipelining instructions comes actually from assembly lines in car manufacturing. Ford, that was his main innovation in terms of car manufacturing. He saw that the way things were working was that all the engineers were working on one car, and then when the car is done, they were like moving on to the next car in the assembly platform that they had, like in their factory. And then he decided that this is bad, and it's better to have multiple people working on multiple cars at the same time. And that is how they were able to produce cars faster and cheaper. And similarly, that is where pipelining comes into the picture, right? So if you have already broken down the instruction into these subcomponents, and we are going to execute each of those subcomponents in a different cycle, then why not execute multiple instructions at the same time, right? So that is the idea behind pipelining. So here we are breaking down an instruction into 3 components, right? You have to fetch the instruction, you have to decode, and you have to execute the instruction. So in the first cycle, we are going to fetch the first instruction, and then in the second cycle, we are going to decode the fetched instruction. While we are decoding the second instruction, the fetch components in our hardware are basically idle. They are not doing any work, right? So why let them go idle? Instead, we are going to fetch the next instruction in that cycle using the fetch hardware. And similarly, we are going to use the hardware all the time. Like all components of the hardware are being used all the time, but they're all working on different instructions. This way you can execute your instructions faster and you get better performance, right? So that is the key idea behind pipelining. So what pipelining essentially does is it is a bandwidth improving technique, right? So before, let's say in a single cycle design, in every cycle you are executing one instruction, right? So that's how we were getting performance. And then in a multi-cycle system, we were taking few cycles to execute one particular instruction. But in a pipeline design, you're going to execute many more instructions in the same number of cycles. So your instructions per cycle goes up with pipelining. So that is a throughput measure, right? So we are measuring the number of instructions executed on average in a given cycle. So that will go up, and that is the measure of like your bandwidth. But the downside of pipelining is that if you take any one instruction in your instruction stream, that might take a little longer to execute than in a case where you didn't have pipelining, right? And the reason for that is all the additional hardware that you need to add into your pipelining structure to hold on to intermediate values, to check for dependencies among instructions, and all these other things, right? So if you look at this figure here, so on the top we had, let's say we have one cycle in which we are going to finish all the work that belongs to an instruction, right? So then, and then let's say that it takes us n units of time to finish this amount of work. Then the bandwidth that you are getting is essentially 1 over n, right? And but now if you add another pipeline stage, and then you basically break down your work in half, then each of your pipeline stages will take n over 2 units of time, right? But still every cycle you are going to retire an instruction, right? But the cycle time is now gone down to half of what it was before. It was n, and it is n over 2 now, right? So the bandwidth will approximately become 2 over n. So you have doubled your bandwidth by having 2 pipeline stages instead of having 1 pipeline stage, right? If you are able to make your pipeline stages smaller, and let's say they each take 1/3 of the time as the original thing, then your bandwidth is going to be tripled, right? You're still, so the thing to wrap your head around is that you're still going to commit or finish executing one instruction every cycle. It's just that the cycle time is going to reduce as you make your pipeline stages smaller and smaller, right? But if you look at any individual instruction, in this case, it has to go through 3 pipeline stages. That means you'll have to have at least 3 internal registers between the pipeline stages that are going to hold the values that are needed to perform the computation which is going to be performed in that particular stage, right? So all these extra logics that you're going to add is going to add some more time to your design, right? So if you take any one instruction in this design, it's going to take n units of gate delay, just like the original design, but there we are also going to consume some time for these logics, extra logic that we are trying to add, right? So your cycle or the time taken for any one instruction keeps increasing. So the latency that we incur when we when we execute an instruction keeps increasing as we add more pipeline stages, but that is fine because we are able to increase bandwidth as a consequence of this mechanism, right? At the end of the day, what you care about is the number of instructions you are able to execute in a given time. You don't really worry that much about how long is each individual instruction taking to execute, right? So pipelining essentially trades off some latency to get much higher bandwidth, and that is the optimization that works here, right? So this is the classic 5-stage pipeline. We fetch an instruction, so it is obviously broken down into like 5 stages. We fetch the instruction, and then we decode the instruction, and then we execute the instruction, and then we issue any memory accesses as part of the instruction, and then finally once we have the values, we are going to write back the values back into the register file, right? So if it took you t base amount of time to execute the entire thing in one clock cycle before, the new clock cycle, because we have 5 pipeline stages, is going to be t base over 5, right? Any questions? Yeah.
Is it possible for an instruction to skip a stage? So let's say if you have an instruction that doesn't need to write to memory.
Mm-hmm.
Can it skip a stage and like really have a shorter stage for instructions? Is that like possible?
No. So these kind of pipeline designs are called in-order pipelines. So here every instruction has to go through every stage. When we get to out-of-order processors, you will see that some instructions will incur like less time to finish, while some instructions take longer. Yes. Yeah.
So in the previous slide, there must be a limit for where there's a point that the bandwidth compensation will be equal to the delay taken with the pipelining will be equal to the delay with one cycle. Because adding more logic.
Yes. So what you are saying is that there will be a end point to this where we can't like pipeline further, right? So that actually comes much before the logic that we are adding becomes a bottleneck. So if you wait for like till the end of the lecture today, like that will become more clear. But what you are describing is a logical endpoint. But because of how our programs are written, there is a much earlier endpoint where pipelining becomes useful, right? You can't pipeline. The limit to pipeline is like much earlier than the point that you are describing, and you'll see why that is the case. Yeah. Okay, so let's go over each of these stages, right? So can somebody tell me what happens in fetch? What are the things we need to do in the fetch stage?
I think the instruction address or something is being pulled out by
The instruction address is being pulled out.
and then probably the is it
So you're heading in the right direction, but is there a place where we store the instruction address? Like you can raise your hand if you want to speak. I heard the correct answer. Program counter. Okay, yes. So the program counter is a well-defined place where we have the location of the address that is going to be executed, right? So, okay, now we know where the instruction resides. So what does fetch do? The answer might be obvious.
Yes.
So don't overthink this. Like this should be like fairly straightforward. Sorry, what did you say? Nothing.
Fetching the instruction from the disk and bring it to the RAM.
Okay, so that's a very good answer, but that's a good answer in an operating system class. So in a computer architecture class, we are assuming that your program has already been loaded into memory, right? And I guess the answer is that you have to use the PC to go to memory, look up memory, find the instruction, and then you get it into the processor pipeline. right? So we are assuming that your operating system has already set up the program. Like we don't have to worry about those kinds of things, right? And the next thing that we have to do is we have to increment the PC, right? So that we know where the next instruction is, and then we can go grab the next instruction in the next cycle, right? We are assuming no branches, but if you have branches, then you have to somehow figure out what is the target address of the branch, and then you have to fetch your instruction from the target location. So you have to update your PC to point to the target location, right? Okay, so what else do we have to do in the fetch stage? You have fetched the instruction, great. You have incremented the PC.
We have data, we need to calculate the address.
In the fetch stage,
I guess.
so we don't work with data in the fetch stage, right? Yes, and you are disqualified from answering this. Yes. Any other answer? So if you fetch the instruction, so what do we do?
We split it into opcode, and then we give it to the next cycle so that each one, I mean the length of each, the opcode and the target address.
We don't yet have the target address, right? That will come later, but you are going in the right direction. So the next thing is to write down the instruction into, like you have to figure out what are the different parts of the instruction and then write them down into your pipeline register, so that the next stage in the next cycle, decode, can figure out what this instruction actually is and perform its duties, right? So apart from doing the work that that particular stage is supposed to do, like fetch is supposed to fetch the instruction, right? So that is to be expected. All stages have to do the work that is necessary to set up the next stage to do their work, right? Okay, so looking at this pictorially, you have the program counter, right? And there is the instruction memory, or you can think of it as the instruction cache, where your instructions reside, right? So we use the program counter to look up the instruction memory to figure out what is the instruction, right? And at the same time, we are going to increment the PC by 1, or like PC++, you increment it by how much ever your instruction size is. And this is where your ISA plays an important role, right? So if you had a fixed length ISA, you know exactly how much to increment by every time, and your hardware is much simpler. But if you have a variable length ISA like x86, now you don't know exactly how much to increment your PC by. Like you have to do you have to go look at the instruction itself and use some information that has been encoded in the instruction to figure out how much to increment your PC by. So you can see how a variable length ISA already makes your hardware a little bit more complex than a fixed length ISA, right? Okay, so we have incremented the PC and we are going to write that into the PC. So we are going to increment the PC and then write that value back into the PC register here, right? So why do we have a mux there?
Because of brand.
Yes. So we are incrementing the PC in the common case, but when you are executing a branch instruction, for example, you have to find the target address and use the target address to update your PC, right? So the target address is going to be calculated down the line in the pipeline. So somebody else is going to provide the value, but for now we can assume that the value is going to come and the correct value is going to be provided. Like we don't have to worry about that at this point, right? So next we have the pipeline register that is going to feed the next stage in the pipeline, which is decode, right? So if you see some notation like this, instruction fetch / instruction decode, that is the pipeline register between fetch and decode. Like we are going to follow a similar convention for all the different pipeline registers, right? So we are going to write the PC+1 value, right, or PC++ value. Can somebody tell me why we are providing the PC++ value to the next stage in the pipeline? Yeah.
If you want to do a jump with an offset, so then you can use the LOU to calculate what the offset is.
Yes. So we looked at in the different kinds of ISAs that we studied. We saw that some instructions are based on the PC offset based addressing, right? So the target address is provided as an offset of the current PC, right? So the offset provided has to be added to this incremented PC value to find the target location for your branch, right? So for that reason, we have to pass along this incremented PC value until the stage where we are going to compute the actual branch target address, right? So as you can see, we are doing the work of fetching the instruction, and apart from that, we are doing all the work that is necessary to set up subsequent stages in the pipeline to do their job, right? So that is what we do in the fetch.
Shouldn't the current value PC rather than the next PC?
So that's the thing. So it is based on convention. So offsets are written based on the PC++ value. You can use either, right? Like it doesn't matter. You've already calculated this value, so you can use it. Anyway, so you're going to get the blue arrow there represents that we are going to get the value for branch target address if we need to use that in the next cycle to fetch, right? So this is all the work that is done during fetch. Any questions here? Yeah.
So the pipeline register, it said that it has to be edge triggered.
Yes.
Is that purely due to optimization or?
No, so that's how pipelining works, right? So if we are going to perform some work in this cycle during fetch, we are going to start updating the values in the pipeline register, right? So if this were not like edge triggered, and if these other cycles, other pipeline stages can read the values that we are writing here, then you will see intermediate values which they are not supposed to see. So the idea is that we are going to start writing, and if there is an edge trigger, the values will be latched on here at the end of the cycle, right? So once all of the work is done, the values are copied and held constant in the latch. So that is the reason why we use edge triggered latches, right? Any other questions? And this is true for all pipeline stages, right? So all of the work that you are doing in the cycle will produce intermediate values, and only once when all the value is done, you want the values copied over into the pipeline register so that you can use it in the next cycle.
It's never level triggered.
If it's level triggered, then for half of the cycle, like it will remain the same, like it will be functional, and you don't want that. Okay, so we fetch the instruction. What does decode do? Or what do you think decode must do? Yeah.
Figures out the values of the operands, if there's any.
Yes. Okay, so you figure out what the operands are, and anything else? Yeah.
Set the value for merge selector in the ALU.
Okay, so what you're saying is that there could be multiple possible inputs for the ALU. Like the ALU could be getting a value from a register, or it could be getting a value from an immediate value in the instruction itself, and you have to set the appropriate control bits so that you're getting the right value, right input, right? Okay. Anything else?
Fetching the operands?
Fetching the yeah, that's what she said, right? Yeah. Anything else that we should do in the decode stage? So this was something that I said every stage must do.
Trying to do the pipeline register.
Yeah, so you have to basically set up the next stage, right? So you have to write the necessary fields or necessary components of that instruction into the next pipeline stage, right? So that is still the responsibility of decode. So first we are going to decode the opcode bits to figure out what is the instruction that we are trying to execute, and to also understand what are the control signals that we are going to set up for ourselves and for later stages, right? So we're going to do that, and then we are going to read the input operands from the register file, right? So that is going to be specified by the instruction itself. So the instruction is going to specify that what are the two registers you should read from, or if it needs only one register input and the other is immediate, all of that information is going to be present, and it is the responsibility in the decode stage to figure out what your input operands are. And then finally we have to write to the pipeline register for the next stage. So we have to write the opcode so that in the next stage the ALU can perform the necessary computation. Like the ALU needs to know if we are doing an add instruction or a subtract instruction or a multiply instruction. so on, right? And then we have to provide the register contents. We have to provide what are the offset and destination fields, because eventually in the write back stage we are going to write back to the register, to the destination register, right? So what is the destination register? That information should be decoded and passed along in the pipeline stages, right? And then we have to propagate the PC+1 or PC++ value so that future stages, whoever is doing the branch target computation can use that value. Okay. So if you look at the diagram, we got the instruction bits and the incremented PC value from the fetch stage. And we are going to decode the instruction bits to figure out what are the input operands, register A and register B by convention. And then we are going to read out those values from the register file and put them into the next stage of the pipeline. And then we are going to read the incremented PC value and then simply propagate that to the next pipeline stage. And then we are going to look at the control signals based on the instruction encoded instruction, and then we are going to provide that to the next stage as well, right? So this includes things like your immediate fields and other values which the ALU would have to use. Right. Any questions on decode? Yes.
What happens during load store? Because it will be a memory fetch. I mean, the operands have to fetch from memory.
So we'll come to that in the memory stage, right? So this is, we are still in the decode stage. Any questions on this? Okay. So the blue arrow on top represents the branch target address that we were supposed to get and send back to the fetch stage. So that is flowing along. And then what you are seeing here, the other blue arrows, these are mostly done, so these blue arrows are for the write back stage, where we are eventually going to perform the computation and we know the destination register that has to be updated, right? So those will come back and be updated here. That is not work we do in the decode stage, it's in the write back stage, but because this is where the components are, I'm just showing you the entire data path of the system, right? Okay. So execute. So what happens in execute? Any guesses? The name should tell you something. So anyone? Yeah.
ALU regarding the control bits will do the operation, the operation on the value of the registers.
Yes. So by looking at the control bits and the opcode, the ALU will perform the necessary computation. Anything else that happens here? Yeah.
Writes the value of the output register in a temporary buffer.
Temporary buffer?
I mean, because finally it will be written by write back stage.
Yes. So how will we get things to the write back stage? You're right, like it's a temporary buffer, but it has a very specific name. Anybody else? No guys, this is much simpler than you are like thinking it is. You'll just write it to the next pipeline register.
EX/.
Yeah, right. So that's the pipeline register to which you're going to write it to. Anything else that we do in the execute stage? Yeah.
It also computes the branch address.
Yes. So if you have a branch instruction, we execute or we figure out what is the target address for the branch in this particular stage. If you are a memory instruction, is some work done for you in the execute stage, or is no work done for you? Yeah.
Final target address?
Target address for the memory that we are going to look up or either write to, that location is also figured out in this stage. Anything else? Okay, no, I think that's it. So now we are going to, in this stage we are going to perform the ALU operation. So So we know what the input operands are that are already provided to us by the decode stage. So we are going to use that value. And which input values to exactly use is also determined by the control signals. And then if we have a branch instruction, we also figure out what is the target location by adding the offset field to the PC. And then we are going to write all the necessary state to the next pipeline register. So the result of the ALU and the contents of register B, or it doesn't have to be register B, but one register is going to be written to. So why are the contents of one register being written to the next stage? So we've already used them up as inputs, right? So why do we have to pass along the contents of one of the registers to the next pipeline stage? Yeah?
Is it because of the, if there are two operands, then the result is written to the first register?
No. That's not true. So write back stage takes care of the ALU result, right? So we are passing along the ALU result, but we are also passing one of the inputs to the next stage. So why would we pass one of the inputs? Yeah.
Maybe it can be the results register. The register.
We are writing the result, right? Or you are saying the value of the destination register? We never read the value of the destination register, right? You only read your input registers, and then you are going to write to the destination register eventually. You never read the destination register. So, and register B is one of your two inputs, right? We said the two inputs are register A and register B, and we are passing along one of the input registers. Yes?
It's one uploaded into memory or stored in memory.
Exactly, right? So if you have a store instruction, the way store instructions work is that the target address to which you are writing to as part of the store instruction is provided using one register, and the value that you're going to write to is provided using the other register, right? So the contents of this register are presumably the values that you're going to write in the memory stage. So we have to pass along these values to the next stage, right? And we send along the instruction bits for the opcode and the destination register so that the next stages can do their operations correctly, right? So if you look at the figure, it's fairly straightforward. Let me just go through the entire animation and then we can walk through these different things. So if we look at the ALU, it has two inputs. One is always the contents of register A, right? And the other is a mux between the contents of register B and the control signal. So the value that is coming out of here is basically the offset field, right? Or the immediate value. So we either select the contents of register B or we select the immediate value in your instruction as the second input for the ALU, right? So that again depends on what kind of instruction you're executing, right? And similarly, if you have a branch instruction, right, we are going to add PC plus 1 to the offset field, which again comes from your control bits as part of the instruction opcode, and the resulting is your final value of the branch target address, right? So if we look at what are all the things that we write so that into the pipeline register exmem so that the next stage can use it, you'll see that we have the branch target address up top, and then we have the ALU result so that write back can use the ALU result, and then we write the contents of register B so that if we are executing a store instruction, that can use these contents to update your memory, and then we also write all the control signals that are necessary to perform the next operations. Right? So the next stage still needs to know if it has to do a load access or a store access, right? So all of that information is still propagated through the control signals. And the blue arrows that you're seeing at the top and the bottom, the top one is the branch target address that we're going to send back to the fetch stage, and the bottom two here are the destination register and the value that you're going to write into the destination register that is being propagated from the write back stage back to your decode stage, or back to your register file. That's where the value is, right? Any questions? Yeah.
Why do we need to pass the PC plus 1 with the offset, even though at this point you know we either branch or not? So why don't we just pass it out to the mux that determines the next PC value?
So we are going to send the value back, but you can't send the value back directly from this like logic, because this is combinational logic, right? So it is doing the work during the cycle. So the value is not held constant for you to use wherever you are using it. So we'll pass along the value into a register here, which is edge triggered, and then we're going to pass the value back so that it will stay constant during the entire cycle. Right? Any other questions? Okay. Okay, so what do we do in the memory stage? Okay, now I'm going to randomly pick people, I think. So what happens in memory stage? Yep.
We load or store from the memory.
Okay, fairly straightforward. Anything else that we do in memory stage? So what if you were actually executing a add instruction? How does the memory stage help you?
Just pass the arriving operation.
ALU result.
Yeah.
You just propagate the ALU result to the next stage so that write back can write eventually, right? Yes.
Do we check the address bounds here or not? Because if the instruction is reading or writing to the address, that's not really
So the more sophisticated, like out of order processors, they do stuff like this, but not in a 5-stage pipeline. But if you were to implement a bounds checking, you would do that here. Right. Anything else? No. Okay. So we simply perform, we access the data cache or data memory to perform the load or stored instruction, right? So the control bits that we got from the previous stage tells us, oh, if you have to do a read or a write, and it will set the necessary enabled signals for you to do the operations. And then we are going to propagate the ALU result that we got from the previous stage to the next pipeline register so that we can eventually write it back. And for a load instruction, we'll look at the data that we received from the cache, and then we are going to pass that along so that the value of the load operation can be written to the destination register, right? One thing to note is that a store instruction does not produce any output, right? In a store instruction, you're taking a value from a register and writing it to a memory location. You don't update any particular of your architectural registers, right? So there is no value for us to like write back in a store instruction, right? And then we pass along the bits from the opcode, and especially the bits which specify what the destination register is, into the next pipeline register, so that when you're doing the write back, you know exactly which register to write, right? So this is what happens in the ALU, memory stage. We simply directly propagate the ALU result from the previous stage. And then for all of our memory operations, we are going to use the contents of register B, which is the value that we have to write as part of the store instruction. And we are going to use the ALU result. So why are we using the ALU result? To look up memory. Yep.
They would try to read the address in memory.
Yes. So the ALU result tells us exactly the memory location that we are going to access, right? So we know the location to access, and if it's a store instruction, we know the data to be written. So now we have all the information that we need to go look up memory, and then we're going to do that. And for a load instruction, we are going to get some value back from memory, and that is going to be written to the memory write back register, right? And then we are going to pass along the control signals so that whatever work needs to be done in the write back stage can be performed using these signals, right? And then now, like you were saying before, we are going to see what is the target address, and then we are going to send that back so that we can use it to figure out what next instructions we need to fetch, right? And these are the two values that we've been propagating backwards, your destination register and the value of the destination register, so that we are going to send back in the write back stage, right? And is there anything else we need to send back in the stage? Sorry? So that we are already sending back, right? That's the top blue arrow. You mean the program counter for this instruction?
No, for
Yeah, if it's a branch instruction, right? So that we are already sending. Is there anything else we need to send? It is related to the branch instructions.
Instruction after the branch.
The address of the instruction after the branch? No, that we don't have to send.
Should the branch should be done or not?
Yes. So we have to send a control signal which specifies to the fetch stage if it should use the target address that we are sending from here, or if it should use the PC++ value that it can locally generate, right? So based on the conditions of your branch instruction, if the conditions are met, you're going to take the branch. If the conditions are not met, you're not going to take the branch, right? But irrespective of whether the branch is taken or not, we are going to compute the target address. But apart from figuring out what the target address is, we are also going to figure out if the branch is taken or not. And that information has to be propagated back to the fetch stage, so that the fetch stage knows if the branch is taken or not taken. And if it's taken, what is the target address, right? So we need to provide both sets of information, and we are going to do that, right? Okay, what happens in write back? You have answered some questions, so I'm going to pick somebody else.
writing the registers to the output.
So, okay, so one convention, that's correct answer, but one convention is raise your hand before you want to speak, so that I can pick different people. But yes, we are going to write back the results that we have generated back to the register file if necessary. Like a store instruction doesn't require you to write anything to the register file, so we don't have to do anything there. But if it's a load instruction, we are going to write back the value that we got from looking up the data memory or data cache, and then we're going to send that back to the register file. If it's an arithmetic instruction, we have the ALU result that we are going to write back to the destination register, right? And we are going to look at the opcode bits and then set the enable bit for the particular destination register, so that we can write the value to the destination register and not any other register, right? So it's fairly simple. So we have all these data that we have generated as part of the instruction, and we have to send that information back to the register file along with which register should be actually updated, the destination register, and all of this information goes back, right? And we also set the enable bit for the corresponding register so that it can capture the new value that we are trying to write. Yes?
I have a question about the mem stage.
Okay.
Bring back. Thank you. Why don't we need to pass the PC plus one offset to the mem mem write back stage register? Because all of the instruction needs to pass all of the stages.
So the instruction is passing, right? Like if you take an add instruction, it will go through all these stages, and it will go to the write back stage, right? So we are controlling what is the information that we are sending from one stage to another stage, right? So if there is any value for sending the target location for the branch to the write back stage, then we would propagate it. If there is no value, then there is no reason to propagate it. Like if you're not going to use that information in the write back stage, why should I propagate it to that stage?
Because
so now the question is, do we see some value for sending along this PC plus 1 plus offset, like the target address, to the next stage. Can we do something with that in the write back
No,
stage?
we don't need this in write back stage.
Yes.
But every instruction needs 5 cycles to be done.
Yes.
Doing so means that the branch instruction will be happen in just 4 cycles.
No. So your branch instruction will be executed here. You will send back the address, and it will spend 1 more cycle in the write back stage. It just happens that there is no work being done for the branch instruction in the write back cycle. Right? So the instruction will spend a cycle in the write back stage, just that there is no work to be done for that particular instruction in that cycle. Right? So this is similar to an add instruction, right? So what is the add instruction actually doing in the memory stage? We're not doing any work for the add instruction. It is just going to spend or waste 1 cycle in the memory stage, and then in the write back stage its value is going to be written back.
And it is done in 5 cycles.
Yeah, and branch also will take 5 cycles. It's just that all of the work needed for the branch instruction finish in the first 4 cycles, and the 5th cycle is just a wasted empty cycle for the branch instruction. Right?
Can we not optimize that by not making it in order?
Yeah, that is the point of out of order processors, right? So it is not only that we are losing 1 cycle for a branch instruction here, it is that there are lots of cases where things or instructions which are lower or like downstream from your instruction, like your current instruction, which can be executed, but in an in-order pipeline you only execute things in order, right? So you might have a case where if this is the instruction stream, like these are all the instructions that you're executing starting from here, in an in-order processor you're going to execute these things in this particular sequence, right? But it might happen that these instructions are not at all dependent on these 2 instructions, right? They can be completely independent instructions, and we can actually execute them when, let's say, if these instructions are taking a long time to finish, right? But an in-order processor does not allow you to do that. Right? To give you a more concrete example, let's say this is a load instruction that missed in the cache, it has to go to memory, so it's going to take a long time to complete. And later you have some add instructions, very simple add instructions, which are not dependent at all. They're all reading different registers and writing to different registers. So there are no dependencies between the load instruction and these set of instructions. In an in-order processor, you're forced to wait until the load instruction is done, and only then can you execute these other instructions. Right? But an out-of-order processor allows you to execute these instructions while you're waiting on the load instruction, so that you're performing useful work when you're waiting on the load instruction, and in an in-order processor you would do nothing but stop. Right? So these are motivations for why we came up with out-of-order executions, and this thing where some instructions, all instructions have to take the same number of cycles to execute, even though in some of the stages they don't do any work, is one of the motivations behind out-of-order process. Right? But the dependency-based stalling is like the more important reason for why we have out-of-order processors. Right? Yeah.
So let's say we want to add R1, R2.
Mhm.
We say load R1.
Okay.
Right? And then load R2. But by the time we say load R2, add has already entered the pipeline. Will it enter with the old register value or?
Sorry. So which?
So let's say you have load R1.
Okay.
Then load R2.
Okay. So the destination register is R1 for the load, and the next instruction is load R2.
Yeah.
So we are writing to R2. Okay.
Then add R1, R2.
Okay. So this is write to R3, R1 plus R2.
Yeah.
Right?
So if add already enters the pipeline before load R2 is complete.
Mm.
Is that possible?
In an in-order?
Yeah.
No. Right? Like things will enter the pipeline in order. You cannot push instructions into the pipeline out of order. Right? That's the whole point of in order. When you say in order, things will enter the pipeline in order. So in this case, it will be load, and then add. And what we are going to talk next is you're going to see that, or the hardware is going to observe that the add instruction here has a dependency on these previous two load instructions, and we are going to either stall this add instruction until R1 and R2 are ready, or we can do some fancy techniques like forwarding the values from R1 and R2 as soon as they are available and then send them to the add instruction. So we are going to see all of those.
So if there is that dependency, it doesn't even enter the pipeline. Add will not enter the pipeline.
It will enter the pipeline, but it will stall or when we know that we don't have the values that are necessary. Right? Yeah.
So when you say stall, do you mean using some type of instructions like no op or?
Yes. So there are different ways to stall. You can actually just hold that thought because these are exactly slides that I'm going to discuss in a few minutes. Yeah.
When does the PC return updated? PC register is updated.
In the fetch stage, we had a PC register. Right?
So we fetch the contents from the PC register, right? Are we writing to it?
Yeah. So let me go back to the fetch stage. I didn't want to do it because it's a lot of yes. So we had the PC, right? So we use the PC to go look up the instruction cache. Along with that, we increment the PC, and then we write the incremented value back to the PC itself. So we are updating the PC register every cycle. We fetch an instruction. Right? Any questions on, let me see if this works. No. I think we're done with this. Okay, so let's, yeah.
In the similar case to this, when there's a dependency on previous statements. Where
Previous instructions. Yeah.
Instructions.
Mm-hmm.
So where does the hardware know that there's a dependency on the previous instruction?
So that's again a good question. So hold on to that thought. Like it probably will be next class when we'll discuss this. But we will build in hardware mechanisms to basically remember what are the registers that previous instructions are writing to, and then we will compare that to the input registers of the current instruction, and if there is a match, then we know that there is a data dependency, and then we're going to stall things. Right? But exactly how we are going to do that, you'll see in the next lecture. Any other question? Okay, so here's a simple piece of code. We have 5 instructions. We have an add instruction and an AND instruction, a load instruction, add instruction, and a store instruction. Like SW stands for store word. So the last register that you see here is the destination register, right? Except for the load instruction, in which case the second register is the destination register. All the registers which are written in red are the destination registers for that particular instruction. So the first instruction adds the values of register 1 and register 2 and then writes them to register 3. The second instruction NANDs register 4 and register 5, writes that to register 6. The load operation looks up the memory using the value in register 2, and we add an immediate value of 20 to that register value and look up the memory, and then we're going to write the value in register 4. The add instruction takes the values from register 2 and register 5 and writes that to register 5. And then finally we have the store instruction, which writes the value which is present in register 7 to the memory location, which is determined by the value of register 3 plus an offset value of 10. Right? So those are the semantics of these instructions, and let's see how each of these instructions pass through the pipeline stages. Right? So this is the fully concatenated pipeline that we have been seeing. We've seen it in parts, so now I've put everything together, and most of the things should be clear to you. One thing, the blue and red, the pink and red arrow here are the destination register and the data that is to be written to the destination register coming from the write backstage, right? So I only drew the data path. I didn't draw any of the control signals propagating, just to make the figure more legible. But as we go along, we'll talk about what are the control signals that need to be present for us to perform these sets of operations, right? Initially, we don't have anything in the pipeline, so all the registers that we have are all the pipeline registers are initialized to 0, but we have a set of values in our actual architectural registers. So R0 is by definition always 0, and R1 to R7 have various values. These are the initial conditions, right? So now the first instruction that we are going to execute is the add instruction, right? So we are going to fetch, based on the program counter, we are going to fetch the add instruction, right? And then we are going to update the contents of the fetch decode pipeline register to include information about this instruction so that the next stage can decode that particular instruction. So if you look at the instruction fetch, instruction decode pipeline register, you will see that the add instruction is present. So this is the instruction that has to be decoded, and we have updated the PC. So it used to be 0 initially, and now after incrementing it has become 1, right? So in the next cycle, what's going to happen is that we are going to fetch the second instruction, the NAND instruction, and along with that we are going to decode the add instruction. So what does decode mean? We are going to figure out that we have to do the add operation based on the opcode of the instruction, and we are saving that here in the pipeline register so that the next stage execute knows what is the operation to be performed, right? And we are going to figure out what are the input operands for this particular instruction, right? So we know that we are going to read values from register 1 and register 2 and pass them along to the ALU in the next stage, right? So the value of register 1 is 36, the value of register 2 is 9. So we are going to send that information. We are also going to send the destination register 3 along. So that is what we are doing here. And we are also sending the value of the third operand, or the third register. The value that is there is also being propagated. We do not need this value for this particular instruction, but if you're passing along an offset value for a store instruction or some kind of an other add instruction, then this field will hold the offset value, and we are going to use that in the computation. So for this particular instruction, we don't really need to use the offset field. So that is just some erroneous data that we are passing along, which does not have any meaning for this particular instruction, right? At the same time, we fetched the NAND instruction, right? And that is being written into the instruction fetch, instruction decode pipeline here, right? In the next stage, if we look at, in the next cycle, in the execute stage, we are going to add the values of 36 and 9. Those were the values that were read out from the register file. And we are going to get the output 45 that we are going to write into the next register, next pipeline register, right? And along with that, now we are going to decode the NAND instruction, right? So we know that the NAND instruction has to read inputs register 4 and register 5. They have values 18 and 7. So those are written into these two fields in the pipeline register here, and you're also figuring out what is the output or destination register and writing that into the pipeline register here. And you're going to pass along the value here, which is not really useful for this particular instruction, but for instructions which have immediate values, that is going to be more useful, right? So an instruction like that is the load instruction, right? So if you look at the load instruction here, we are decoding the values. It is the input register for the load instruction is register 2, which has a value of 9. So we have read the value of 9, and we are going to use the offset value 20 to figure out the effective memory address for the load instruction. So for this particular instruction, passing along this 20 is useful. And when we are computing the effective memory address for the load instruction in the next stage, we are going to use the value of 20 and add that to 9 and we're going to get the value of 29, which is the effective memory address for the load instruction, right? So this is a fairly detailed example without any corner cases. So you can go over it once the slides are uploaded. They're already up, so you can take a look at them, and then if you have any questions, let me know, right? So this is fairly straightforward that you should understand based on all the things that we discussed in this class, right? Any questions here? Yeah.
If we have a branch instruction, can you?
Okay.
If we have a branch instruction, it can be done in just 4 cycles. It can't.
So there is a distinction between when is the work being performed for that instruction and when do you actually consider the instruction to be complete. So you're right, like in 4 cycles, all the work that is necessary for the branch instruction is done. But in a 5-stage pipeline, all instructions take 5 cycles by convention, right? So we are wasting a cycle, you are right. But a branch instruction also takes 5 cycles.
No, I said that for branch instruction, we don't waste that 1 cycle.
So you are saying that
because it can be done in just 4.
So I guess this is a matter of convention, right? So let's say you have a branch instruction and then followed by an add instruction, right? So we have fetch, decode, execute, memory, and then you're saying that there is no work being done in this cycle.
Yeah.
So that is that. But if you look at the add instruction, it will be fetch, decode, execute, memory, and write back.
That instruction never be done.
Sorry?
Because of the branch.
Let's say the branch is not taken.
No, if it's taken, it will be done in just 4 cycles. Because of this architecture.
So if your branch is taken, right, so you will know what is the target address in this memory cycle, and then in the next cycle you will begin the fetch instruction, right, or whatever the add instruction is. Let me think about it. Yes.
And so it is done in just 4 cycles.
Yeah.
Well, I guess if the branch is taken, it's gonna flash the pipeline to load with the new instruction. So we're gonna waste 1 cycle regardless.
Yeah, so that's another issue, right? So it depends on how exactly we are fetching the next instruction. And in the case where the branch is taken, there are other delays that will be involved, like in terms of like flushing the pipeline, like she said. So is the instruction done in 4 cycles? So my main hesitation is that this is not the convention, right? Like when you say I'm executing a branch instruction, are you considering part of like the instruction flushing that you have to do? All those things, are they part of the same instruction? Are they not part of the same instruction? That if you say that my instruction is done here and whatever you have to do after is not part of this instruction, then you could say that it takes 4 cycles. Like that's fine. Yeah.
Yeah, sorry, just want to, I guess he's right. After 4 cycle, we already know the branch target, but the thing is, we cannot just discontinue at that point. So we need to let the pipeline continue by stalling 1 cycle and fetching the branch target in the next fetch
cycle.
Yeah.
Yes. So those things will involve like extra latency, right? So if you consider that, then I can say that the branch instruction actually takes a little bit longer, but it is convention. Right? Yeah. But you're right. Like all the work that is necessary is finished in 4 cycles. Yes.
How is the logic of say fetching the next 3 or 4 instructions in order? Since the PC value is updated at the 4th or 5th cycle, so how is the fetch knowing, like is it like the 3rd instruction should I fetch? Like how does it fetch?
No, so I'm sorry, maybe I didn't understand your question, but every cycle when you fetch an instruction, you're going to increment the PC, right?
But it's getting incremented in the fourth stage, right?
That is only for branches. Only in the case where you have taken branch instructions, you are going to get the target location from that particular stage. But for all other instructions, you are going to increment and use the value here. Right. Any other questions before we move along? No question. Okay. Cool. So these are the time graphs for this particular instruction sequence. So you can see. So the different points here are different cycles that we have in the program execution, and you can see that for each cycle we are, like in some cases, like once the pipeline has been loaded up, we are executing many different instructions. Right? So if you look at cycle 5, for example, we are executing 5 instructions parallelly in different parts of the pipeline, right, using a pipeline processor. This was not true for a single cycle or a multi-cycle processor. And if you have a 10-stage pipeline, then if the pipeline is fully loaded and if you're working, then you'll see that we are executing 10 different instructions in any given cycle, right? Cool. So the next thing that we have to discuss is cycle time for this particular processor, the 5-stage processor, right? So if we didn't have any pipelining, and if we were using a single cycle machine, then the cycle time for that particular processor will be the sum of the times it takes to execute each of these steps, right? So if we are trying to execute all of these steps in a single cycle, then all of the work which is being done in 5 stages has to be done in 1 stage, right? So your cycle time would be 31. Like you add up all of these values, 62959, and then you get 31, right? But in a pipeline machine, we simply look at the maximum value of each of these stages, and that is the time it takes for 1 clock cycle, right? So if you have, so what you are seeing here is that some pipeline stages are 2 units and some pipeline stages are 9 units. So they are slightly imbalanced, and because of that, your cycle time is 9. Right. So your decode stage is finishing all the work that it needs to do in 2 cycles, but since all the pipeline stages have to take the same amount of time, that is how your pipelining works, you will see that we are wasting 7 units of time in this particular stage, right? So is there a way around this? Like how can we not incur? Yeah.
We can divide the max stage into 2, or we can have some of the work of the max stage in either of the stages.
Yes. So what you're saying is that when you have these imbalanced pipelines, we can move work around to make sure that all of your pipeline stages are taking the same amount of time, right? So this can be done using multiple things. One, you can merge some of the work which is done in different pipeline stages, and then say that we are going to like balance the pipelines using that. Or you can divide an existing large stage into smaller stages, and that way you're going to reduce your cycle time. So that is the other way to go about things, right? So deeper pipelines have been a trend, like we have been doing. So when I say deeper pipeline, what I mean is that you have more stages in your processor pipeline, right? So deeper pipelines are like a known technique to increase or to improve your cycle time, but it doesn't always work, right? So can somebody tell me why deeper pipelines don't always work, don't always result in better performance? Yeah?
Like control hazards.
Control hazards, did you say?
So like if you do like an operation after a load that needs that operation, you need to wait for it to finish. But if you have a deeper pipeline, it's just taking more time to wait.
Yes. So when you have dependencies between instructions, what you will notice is that if you have deeper pipelines, you will end up wasting more cycles when one instruction is waiting on another instruction to complete. So you will end up wasting cycles, and we are going to see examples of that, right? The other trends to like doing or balancing pipelines is to have multiple pipelines or sub-pipelines. You will see that once we get to the ALU execute stage, we saw that there is a single ALU in this particular processor. But you might have an ALU unit, you might have a separate multiplier unit, and then you're going to pipeline these two units differently to make sure that your pipeline is in a balanced state. So we'll look at all of these kinds of designs a little bit later. And we also pipeline your memory access. So what you will see is that memory accesses take much longer than one cycle to be fulfilled. So if we have them take up the whole cycle, then the cycle time goes up by quite a bit. So we can pipeline the memory access themselves to make sure that we have a more balanced overall processor pipeline, right? So these are all things that we are going to come back to in like subsequent lectures, right? Okay, how are we doing on time? Are we done? 5 more minutes, okay, plenty of time. So what is the cost of deeper pipelines? So if we have instructions which are dependent on each other, then they can cause an issue, right? So if let's say we have the same 5-stage pipeline, and we have an instruction sequence where the add instruction is writing to register 3, and then we have a NAND instruction which is reading from register 3, right? So this is a classic read after write dependency. So we are reading the value which is being written to by the previous instruction, right? So now if you look at the NAND instruction, it can be fetched and decoded, but before we can execute, we have to wait till the write back of the previous instruction is complete, right? So that means that we have to wait for a couple of cycles, or we have to stall for a couple of cycles for this instruction to be executed in this pipeline, right? Now imagine a case where we had a much deeper pipeline, let's say 10 stages, right? The write back is still going to happen in the last cycle, right, in the 10th cycle, and you're trying to decode or execute the instruction in say 4th cycle, right? So now you have to wait 6 cycles. Cycle 10 is when this instruction is going to provide the value, and we were ideally going to start executing in cycle 3 or cycle 4, like based on your pipeline stages, but now you have to wait until cycle 11 to get the value that you're going to use, right? So you've wasted 6 cycles. So when you have longer pipelines, there is a potential for wasting a lot of cycles in just waiting for previous dependencies. This is not just for data dependencies, you will have this for control dependencies as well. So if this instruction were a branch instruction, right, it might take you 8 cycles to figure out this is a taken branch and I have to go somewhere, right? So now to fetch the next instruction, I have to wait 8 cycles, know what is the target address, and then only can I go and fetch the next instruction, right? So I wasted 8 cycles. Whereas in this shallower pipeline, where we have only 5 stages, we wait only 4 cycles, right? So based on how deep your pipeline is and where your branch resolution is happening, you might have to waste a lot of cycles as well, right? Did you have a question?
Considering like the cycle time in deeper pipelines with respect to like shallower pipeline,
Yeah.
isn't it comparable?
No, so your cycle time improves, but what you'll see is that because of these dependencies, these lost cycles will start to dominate and you end up losing performance, right? So this has happened in practice as well. Like Intel produced like very deep pipelines, and then they found out that they're actually losing performance compared to shallower pipelines because of all these dependencies, right? So that is why there has been like a significant slowdown in the number of pipeline stages that we were adding. Right. Okay. So, we are almost done. So this is a good place to stop. We'll pick it up from next class.